Hey everyone, welcome back. In this video, we'll be discussing about the third problem of yesterday's biweekly contest, find the maximum sequence value of an array. The problem is really interesting, as in this problem doesn't require you to do usual memorization with recursion, rather want you to explore all possible different values to get to the answer. Because the problem is a bit difficult one, there are times where I will not be doing a complete dry run of the solution. So I would give you enough pointers so that you can do it by yourself. I would encourage you to pause at that section and do a dry run to understand the solution better. Having said that, if you stick till the end, I'm very sure you will be able to understand everything that's behind this problem. So let's get started. The problem states that you're given an integer array nums and a positive integer k. The value of a subsequence of size 2 cross x is defined as the OR of first x element and OR of last x element. You store them up, that's the value of your sequence. Now, your task is to find out a subsequence of size 2 cross k such that its value is maximum possible. So let's take an example. Let's say the nums array is 4, 2, 5, 6, 7 and k is 2, which basically means you have to select a subsequence of 4, 2, 5, 6, 7 of size 4 such that its value is maximum possible. So one of the ways to select 4 different elements is 4, 5, 6, 7, right? And the value of this sequence would be 4 or 5, which is 5, 6 or 7, which is 7, and you XOR 5 and 7, which becomes 2, and the value of this entire sequence would be 2. Now you can try out other possible sequences. You will not be able to get a value greater than 2, and hence the answer here is 2. So hope the problem statement is clear. Now, one of the brute force way could be simply try out every possible subsequence of the array, find its value, and get the maximum value. But obviously that solution will not work because that would take order nc2k time. But the value of n here is 400 and k can also go all the way up to, like 2k can also go all the way up to 400. So the value of nck is very huge here, and hence you can't simply try a very brute force solution, right? Now, whenever a solution or the question of this bitwise operator come, how I usually proceed is try solving the question for 1 bit integer and then try to derive some sense out of it. Again, this is how I proceed. If you have some other solution, please feel free to post them in the comment section so that I and others can also learn from that. So we have a 1 bit array, that is every number is either 1 or 0, and we want the XOR to be maximum. Now because the numbers are 1 bit array, the XOR can either be 0 or it can be 1. Now we want maximum. So the obvious approach could be, okay, let me try out whether I can get a XOR of 1 or not, right? Now, how can you get a XOR of 1? You can get a XOR of 1 by either XORing 1 with 0 or XORing 0 with 1, right? What does it mean? It means that let's call this entire thing left part and let's call this entire thing right part. So what you are saying in turn is the left part should be 1 and the right part should be 0. If you can achieve this configuration, or in other words, you can say if I can select 3 elements such that the OR of those 3 elements is equal to 1, and after that I can select 3 more elements such that the OR of them is equal to 0, then I can say I can get a XOR value of 1, right? Similarly, if this configuration is not possible, that is you can't select 3 elements to make the left part equals to 1 and the right part equals to 0, you can try out another configuration which is 0, 1, which basically says the same thing in just opposite fashion. Now you might be thinking whether it is really required to try out all the configuration. Can we simply say that if I have tried out this configuration, I am done? Answer is no. Why? look at the second example. In this case, you can't get this particular configuration at all. Why? Because to get this configuration, what we are saying is I want 3 elements from the left which will OR up to 0. In turn, we are saying that I want 3 0 elements. So these are the only 3 0 elements. Now if we have taken these 3 0 elements for the left part, this entire part of the array you have spent for the left part itself. Now for right part you just have 1 element, but you need to select 3 elements such that their OR value is 1, but you can't do that. Hence you can't have this particular configuration, but you can have this configuration. If you just see here, you can easily select these 3 elements for the left part and these 3 elements for the right part, and the left part OR value is 1 and the right part OR value is 0, and hence this configuration is achieved and you can still get a XOR of 1, right? So basically what we have seen here is it's not possible to say that I will try out only one configuration, and if that configuration is success, I can achieve it, otherwise I can't. So we have to try out every possible configuration here. That's pretty clear. Now think about it. If you can get one of these configuration, then okay, the XOR is 1, otherwise the XOR is 0. For example, the third example here, in this case the XOR is 0. No matter what you do, you will not be able to achieve this or this configuration, and hence the final XOR value will not be 1, which in turn means it will be 0, right? So what is your approach? Approach is I will start with the maximum XOR value that I can have. I will divide it into its constituent left and right part. For each combination, I will check whether that exists or not, or that is feasible or not. How to check, that's a different story, we'll come to that, but we'll check if that is feasible or not. If it is feasible, then the current XOR value which I have picked is feasible. If all the configuration for the current XOR value is not feasible, I will try out the next possible XOR value and see if that is feasible or not. So let's just increase one more bit to just look at the complexity of this entire approach. So if you increase one more bit, the best XOR value would be 3, right? You will, for 3, these are the different combinations. If any of these combinations are not feasible, then you will try out the next best XOR value, which is 2. 2 has these combinations. If any of these is not possible, then you will try out the next best XOR value, which is 1, and then 0. So if you think about it, or if you look closely here, you are trying out every possible left and right value in a way. For example, let's say the actual XOR value feasible for this example is 0. In that case, you will try out all these 4 configuration, then you will try out all these 4 configuration, then you will try out 4 more configuration for 2, and then you will try out some configuration of 0, and then you figure out, okay, this 0 is feasible, so I will return 0 as the answer, right? So in a way, you are kind of iterating over all possible combination of left and right. You can't avoid that. And if you are iterating over all possible combination of left and right, why even get the burden of figuring out these left and right combination from the XOR value? Why not just iterate over left and right? And if it is feasible, I know that that particular XOR value is something I can achieve, and I can simply take maximum across all of them to get the answer, right? So in other words, this is our overall approach that we will be taking. We will start with all possible left and right values. Why 128? Because the maximum value that is feasible is 2 power 7. So we'll go and find out all possible left and right OR values. For each pair, I will check whether it is feasible to get this pair with k elements or not. If it is feasible, then I know this particular XOR value is also feasible. If this XOR value is feasible, I will simply take maximum across all feasible XOR values, and whatever is the maximum, that will be my answer, right? Now this is a correct approach. The only thing is we need to now worry about the complexity of this part, right? So next we'll be focusing on this part itself. Now before diving into this part itself, or rather let's first define what exactly this means. This means that you want to select the key elements from this array such that the OR of all those elements is equals to LOR, right? And then after this you have to select k more elements such that the OR of all those elements is ROR, right? If this is feasible, this function will return true, otherwise this function will return false, right? Now, isn't this problem equal to this problem? What you are saying is, given an array, I need to select k element such that the OR value is some x. This is also saying, given an array, I need to select k element such that the OR value is equals to x. So both problems are kind of similar. They are just dealing with different array itself. And the array that the left part is dealing with is a prefix of the original array, and the array the right part is dealing with is a suffix of the original array, right? Now, why we are doing this? Just to reduce the number of variables in this entire function. So we are now saying that, okay, if I can solve this part, or if I know how to solve for a prefix, I can apply the exact same algorithm for suffix as well, and I can solve the right part as well, right? So from now onwards, we will keep the left and right part separate, and to keep them separate, you need a separation point, as in you need a barrier that will say, okay, up till this is the left part and this is the right part which I am looking at. Now, what is the right place to put the barrier? Like, you have to set 3 elements, right? So you can place the barrier here as well, or you can place here or here or here. Which of these places are correct? You don't know. So you will try out everything one by one. That is the simplest way. You will say, okay, I will say this is my left part. Can I select 3 elements from this or 2 elements from this? Depends on what the value of k, such that the OR value is a given LOR. And can I select 2 or k elements from the remaining array such that the OR value is ROR? And if both of them returns true, I will return true. Otherwise, I will try out next barrier, which is this. I will ask the same question. Can I select k elements from this such that the OR value is LOR? Can I select k elements from this such that the OR value is ROR? If both of them are true, the entire function will return true. Otherwise, I will try out the next barrier, and so on and so forth. So if I just visualize it in a pseudo code, this is how the pseudo code of IsPossible function would look like. We will try out every possible barrier. For each barrier, I will figure out whether it is possible to get or to select k elements from a prefix such that the OR is this particular value. Similarly, I will check whether it is possible to select k elements from the suffix such that the OR value is this particular value. If both of them return true, I will return true. Otherwise, I will try the next barrier. And if all the barriers are exhausted, I know it is not possible to get to set k elements that has OR value of LOR and then k elements that has OR value of ROR, and hence we return simply false. So let's keep this for our reference here. Now, what is the new problem? The new problem is we don't have ROR anymore, and we can simply assume that let's start with this barrier. So we can simply assume that this is our array itself. In other words, this entire thing doesn't exist for us at all, and we have 2 variables LOR and k, which means we have to select k elements from this such that the OR of all those elements is equals to this particular value. For simplicity, let's take k as 3 and LOR as 7 for an example, right? Now, can you solve this? This is the right time to pause and try to think about this subproblem by yourself. So before solving this problem, let's try to solve even a simpler problem wherein instead of working with a bitwise OR operator, let's say, can I select 3 elements such that the sum of these 3 elements is 7, not the bitwise OR, sum of these 3 elements are 7. How to solve this? Simple, right? You have 4 elements. Let's just take these 4 elements as their decimal values, which is 4, 0, 1, and 5. So you have these 4 elements. Now you have to select some elements such that the sum is 7. What you can say is, okay, this element I can either take or not take. Now if I have taken one element and I need to take 2 elements such that the sum of those 2 elements is equals to 2. So this problem is exactly equal to the original problem, just with reduced constraint. So you can simply use recursion. You can write a function f that takes in, let's say, index and sum and the number of element that you want to take. Now this function, you can simply call the same function depending on whether what you have done with the ith element. If you have taken ith element, you will simply say, okay, given this reduced array and this reduced sum and this reduced count of element, tell me what is the minimum number of, or what is the, or whether it is feasible to take this particular these many number of elements with this particular sum or not. Otherwise you will simply ignore the current element and say, okay, now with the remaining array, tell me if I can select k elements that has sum up to s. So you can simply apply recursion to solve this problem. Can you do the same with the sum replaced with bitwise OR? Answer is no. Why? Because you can't, like in this case, you are able to derive a independent subproblem from the original problem. But in this scenario, but with bitwise OR, you will not be able to derive a independent subproblem. So if you think about it, let's say this is bitwise OR instead of sum. So you want a bitwise OR of 7. So what do you mean? What do you want? You want 1, 1, 1, right? Now let's say you decided to take this particular element. Now if you take this element, you can't say that this particular bit is satisfied and I only want these 2 bits. In other words, you can't say that, okay, with this remaining 3 elements, I just want a bitwise OR of 3. This will be wrong. Why? Because if you just ask for bitwise OR of 3, you will never be able to select this particular element which has a value of 5. But you can see you will only get bitwise OR of 7 if you select these 3 elements. But if you remove 1 altogether after getting 1 in the first place, you will never be selecting 4, and that will lead to a wrong answer, right? So the difference here is the problem is not independent. That is, if you have got some bitwise OR, you can't say that, okay, I got some bitwise OR, I will not take any element that still has this particular bit set. That is not feasible, because if this bit is set, that will be a no op for this particular bit, but you can still utilize other bits of that particular number, right? So because the problem are not independent, or the subproblem is not independent from the original problem, you can't apply recursion here. That's the very important part of the problem. Now if you can't apply recursion, what's the other strategy? The basic strategy is try out all possible combination. Now what does that mean? This means you try out every possible subset of 3 elements from this entire set of 4 elements. Now if you do this in the naive fashion, this will take you 4c3 time, or in worst case this will take you order nck time, which will not pass, as bad as our initial brute force algorithm itself. So you need to surely optimize this. How? The hint is the total number of, like, you will not be exploring these many combinations, because the total distinct values that you can get is only 128. Now with this hint, I would strongly encourage you to pause and try to see if you can explore all the different combinations of 3 elements with less than this complexity. So hope you thought about it. The trick here is you know that you will be getting 128 distinct element. So you can simply maintain an array of size 128 here, which denotes whether a particular XOR value or whether a particular OR value is feasible or not up till this point. And for the next point, you don't need to do much. Like for the next point, you already know whether a particular XOR value is feasible with the elements in the left side, right? So you are getting a new element here. So what you can do, you can just, if this is feasible, you can XOR it with 2 to get some other element here, right? And if this element is something that was not feasible before, that will now be feasible. So basically you will simply iterate over all possible values and see if you can make it feasible with the new element. If it is, you can set it and move forward. So in that way, you are not trying out all NCK combinations, but you are still able to figure out whether a particular XOR value is something you can achieve or not, right? So let's do a dry run. Again, I would encourage you to pause. If you have understood this, try to do a dry run and try to write a pseudo code by yourself from this point onwards. Again, note that we haven't discussed how to take care of the count of k elements, so you can try that out as well. So let's move forward. We want to figure out whether it is feasible to get a XOR of, let's say, 7 with k equal to 2 for all these from this set of 5 elements. So for simplicity, let's remove k as well. For simplicity, we just want, is it feasible to get a XOR of 7? How many elements? I don't care. Is it feasible or not? Just tell me that. We'll first solve this version here, and then we'll move on to, okay, I know it is feasible, but is it feasible with 2 elements or not? So that question will come, that constraint will add later. So for now, assume that k is also not there. We just have an array which is like 4 2 1 2 3. I need to find out whether a XOR of some x is feasible or not from this array. How to do that? Again, start with the first element. There is just one element. So what are the XOR that is possible? Either XOR of 0 is possible or XOR of 4 is possible. Rest all are not feasible, right? Because either you will not take any element or you will take 4. If you don't take any element, XOR will be 0. So let's say there is 0 as well. So XOR will be 0. If you take any element, you will take 4. That's the only element you have. And XOR of 4 is simply 4. So 4 is feasible. So only 1 and 4 is feasible. Now you come to. So either you take 2 with all possible combinations before, or you simply take 2 with all possible values before, right? They are different things. If you try out all possible combinations, you will end up again having NCK combinations. But instead, the distinct values that you can have is 128 out of all these NCK combinations. So you will simply try out all 128 distinct values that you can have, and from that you can derive what you can get more. So again, 0 is something that you can already have. Now because 0 is something you can have, 0 XOR 2 is something you can also have, which means 2 is also feasible. Now 1 is something that was not feasible, so 1 XOR 3 is also not feasible, right? Now 2 was not feasible, so you can't XOR with 2 to get something. 3 was not feasible, so you can't XOR with 2. 4 was feasible. What does that mean? It means that, okay, with some combination of elements in the left, I can get a XOR of 4. Now, if I can get a XOR of 4, I can add 2 to that combination and I can get a XOR of 6 as well, right? So in the similar fashion, you can try out 5. 5 is not possible, 6 is not possible, 7 is not possible. So you can't get more new elements. But you can still get whatever you had before without including 2. So without including 2, you already had 4. So you can still have it without including 2. So this is your new combination of XOR values or OR values which is feasible, right? Now comes 1. So again 0 is feasible. So 0 or 1 is feasible, which is 1 is feasible. Now 1 was not feasible. So 1 or 1 is also, you will not try. 2 was feasible. So 2 or 1 is feasible, which means 3 is feasible. 3 was not feasible. 4 was feasible. So 4 or 1 is also feasible, which means 5 is feasible. 5 was not feasible. 6 was feasible, which means 6 or 1 will also be feasible. So 7 is feasible, right? And whatever was previously feasible will still remain feasible without taking the current element. So at this stage, you can see every OR value is feasible. So no matter what you do with the next elements, all the OR values will still be feasible. Now, what does this, like once you have built this array, you can simply answer this question just order one time. If someone asks, okay, for this first 5 elements, tell me whether a OR of this 7 is possible or not, you can simply look at 7. If it is 1, here you will say true, otherwise you return false. Now, this entire thing, you haven't taken into account how many elements you have considered to, let's say, make 4. At this point, you don't have any idea how many elements are required to make 4. It could be possible that you have taken more than 3 elements or more than 2 elements to make 4. But it could be possible that you have taken just 1 element as well to make 4. So this part is something you don't have the answer for. So currently we have removed k, but this is the time to introduce k as well. But before that, let's look at the pseudo code for the current part itself, which is without k, with what is the implementation of this IsPossible function. So we will simply iterate over all the indexes and we will try to build this prefix or array by ourselves for every index. Now what we can do, whatever was feasible, you can just simply, like, there are some parts or some set of values which are feasible, right? Now what you can do, you can either add the new element, let's say array of I, to all these sets, or you can keep those elements as it is. That's the only thing you can do. Now because whatever was feasible, you can simply make it feasible. I think there's one more statement here, which is prefix of I should be initialized with prefix of I minus 1, because whatever was feasible will remain feasible, which in turn means that you are simply saying that I will not add a of I at the end to any of my subset. Now the next set of feasibility elements could be, you will add a of I at the end, and that might help you create new elements or discover new OR values at the end. So you will try out all possible OR values. If that was not feasible, it means there is no subset which can make this particular OR value, so you can't do much. But if it is feasible, it means there is some subset which can make you this particular OR value from them. You can add a of I and see if you can get some new OR value. So you can simply XOR it with array of I, and that will also now be feasible. It may be feasible before, but may not be feasible before. So with this, it is now feasible, right? So once you have done this entire thing for all the indexes, this will take you order 2 power 7 multiplied by n. Once you have done this, you can answer this is possible without k, in just order one time, right? And you can do the same thing without k for suffix as well, by just iterating over the array from backwards and calculating the suffix part, and you can also answer that part in just order one time. So just to quick recap, we were started with answering is possible L or R or K. That is it possible to get set k elements from the start? such that their OR values is LOR, and after that select k more elements such that their OR value is ROR. We divided that particular function into this format wherein we say, okay, we will first partition and we will try out every partition one by one. For each partition, I will ask whether it is feasible to get a OR value of LOR from starting to the current partition, and whether it is possible to get a OR value of ROR from the suffix of the partition. Now, for this part, you are saying that you will build this particular prefix array with you, and once you have the prefix array, you can simply go to the ith element of this prefix array, look at the LOR entry here, and if this is 1 or 0, based on that you will return for true or false. In the same fashion, you can build one more version of this array starting from the suffix, and for that from that you can answer this part. Now this both part is now order 1, and you can simply see if they are both true, you will return true, otherwise you return false. Now the main thing is you didn't consider k at all while building this array, so now is the time to take that into account. Now what does adding the constraint of k mean? That means that previously you said, okay, an OR value, you can combine some elements to get an OR of x. Now you are saying that, can I combine exactly k elements to get an OR of x? Now exactly part is a bit tricky here, because you know that you can't divide the problem into subproblem, independent subproblem here. So instead of figuring out exactly part, you can simply figure out how many minimum number of elements are required to get the current OR value that you have, and how many maximum number of elements are required to get to the current OR value that you can have. Now why both min and max, I will leave that to an exercise. We'll discuss briefly towards the end, but you can think about it for that about that by yourself. So now our goal is, along with figuring out whether a particular OR is feasible or not, we will also figure out how many minimum elements are needed to make that OR, and how many maximum element I can use to make that OR. And if min and max is between k, then I can say that, okay, I can select k elements that can give me this particular OR. Which of those k elements, I don't care, because the current problem doesn't ask us that. If that is required, there are other ways to tackle that as well, but for now this should be sufficient. So what we will do, we'll first figure out what is the minimum number of elements required to make a particular OR. So let's start with the same strategy. So 0 is 0, 1 is 0, everything is 0 except 4, and 1 and 0 as well. Like you can also always make an OR of 0, that should be fine. But what is the minimum value here? Let's take entry for 0 as well, just for clarity. This is the entry for 0. So what is the minimum number of steps required to get 0? 0, right? And what is the minimum number of elements required to get 4? 1. You have to take 4 elements to get 1. Rest all are kind of infinity, which basically means you can't get to any, you have to use infinite number of elements to get a OR value of 6, which in directly means you can't get an OR value of 6 with just one element here. Now come the next one, which is 2. Again, the approach is similar. You have some subset which can give you some OR values. You have a new element AI. You can either amend AI to each of those subset, or you can keep AI completely separate, or you can keep those subset independent, and whatever the OR value was, that will remain the OR value. So in this case, again, 0 is still 0. Let's just fill 0 here, right? Now comes 2. So 0, 1 was not feasible. So you can't, basically there is no subset which can has a OR value of 1. So you can't amend 2 to that particular subset. So you will move forward. 2 is not feasible, 3 is not feasible, 4 is feasible, which means there is a subset which has a OR value of 4. You can amend AI, or in other words, currently AI is 2. You can amend 2, and the OR of this entire subset will now become 4 or 2, which is 6. So you can get 6 here. Now, how many steps are required? Previously, you can't get 6 at all, but now you can get 6 with the help of 2. But you get 6 from 4. So minimum number of elements that can give you 4 was 1. And you added one more element to get 6. So minimum number of elements to get 6 is 2. Make sense? So we'll move forward in the similar fashion for 5, 6, 7, everything is 0, so you'll not get new elements. Now you will fill remaining with infinity, except the ones which were already discovered and has some value, which indirectly means that there was a subset or there was an element which you can pick that can give you an OR value of 4, right? So rest you will mark as infinity. In here as well, you will mark 0 except this. Now let's do one last round of dry run for this index 1, which basically mean, okay, I have a OR value or I have a 1, so I can amend 1 to whatever subset you already has, or whatever subset you already has, that will remain as it is. So 0, again, it's 1 already. Now 1, because you can make 0, you can amend 1 to it to make 1 as well, right? So how many steps were required to make 0, or how many minimum steps are required to make 0? 0. You added one more element to make 1. So total number of steps required, or minimum steps required to make 1 is 1. In the same fashion, you don't have 2, so that's fine. You don't have 3, that is also fine. You have 4, so from 4 you can amend 1 to get 5, right? So you can okay, I think I missed 2 altogether here. This should also be 1 because 0 or 2 is 2, and this is also 1 because number of steps required to get 0 was 0, and you added one more element to get 2, so this will be 1. Now 2 is 1, so you can amend 1 to it to get 3, right? So how many elements were required to make 2? 1, and you added one more element 1 to make 3. So number of elements required to make 3 would be 2, and you're able to make 3. Now 4 is feasible. Now 4 you can amend 1 to get 5. Now 5 was infinity, so how many elements are required to make 4? It was 1, and you added one more element, so now you can make 5 with 2 elements. Previously you were able to make 5 with infinity elements, so 2 is still smaller, so you will simply replace this with 2. In the same fashion, this will also become 2, and rest of them will remain as it is. So what does this entire thing denotes? This denotes that, okay, to make 5 you need at least 2 elements with the first 3 elements of the array here. Similarly, to make 7 you need I think this will be 3, right, because it will be from 6. So to make 7 you need at least 3 elements from this first 3 elements itself. Now let's do one more iteration, maybe or maybe I think let's make it 5 and now do one more iteration, right? So after this iteration, this entire thing would be 1. So now it is 5. So you are already able to make 0, so that's fine. You are already able to make 1, so you can add 5 to it to make 5, like 1 or 5 is already 5, right? So you can make 5 by amending 1 to it. 1 you are able to get at one cost, or rather at a set of elements that has just one element, and you are amending 5 to it. So total number of elements now you have is 2. You were able to get 5 at 2 elements. Now you are also able to get 5 at 2 elements. So both are same. So doesn't matter. It will still remain 2. In the same fashion, if you try out 2, you can amend 2 with 7 to get 2 with 5 to get 7. So how many minimum elements are required to get to 1? Now you are adding one more element to create 7. So total number of element now you need to create 7 with 5 is 2. Previously you need 3 elements to create 7, but now you need just 2 elements to create 7, so you will replace it with 2 because 2 is minimum than the previous one. Again, just reiterate this part. We were able to get 2 before. Now you have 5, so you can simply take the subset that has a OR value of 2 and add 5 to this subset, and the OR value of this entire thing would become 7. Now whatever is the size of the subset, you can simply add 1 to it, and that will be another way to get 7. Whatever you had, that's one way to get 7, but now you are getting one more way to get 7. If this way is cheaper than the previous one, you can simply replace it, right? Because we are interested in minimum number of steps. So what does it mean? This means that with first 3 elements to get 7, you need at least 3 elements. But with first 4 elements to get 7, you need at least 2 elements with you. So in this fashion, you can create other things, and you can now answer how many minimum number of elements are required to create a particular OR value with that. So if I show you the pseudocode would look something like this. It's exactly equal to the previous pseudocode. The only thing that changes here is you are now calculating the steps as well. So for array of I, you just need one step, because you can simply OR it with itself, and that will be just one element here. Steps is nothing but the minimum number of elements that you have. So now you will try out every possible previous value, and if that previous value is feasible with the previous subset of elements, then only you will move forward, and you will check, okay, this previous value was feasible with some subset. Now I can OR it with another or current value to get some new value with 1 plus steps of I minus 1 comma previous. Basically whatever was the number of elements that I need to get to this previous value, I just need one more element to get to this new value now. So I can simply take min across whatever was the number of ways for that new value and the current value that I have. If we keep doing this, at every position we'll have what is the minimum number of elements required to get to that particular OR value from the first I elements of that array. Now in this similar fashion, you can create max as well. Let's call this min steps. In the similar fashion, you can create max steps as well. In that case, the only difference is instead of min, you will simply create max here, right? So in that case, this 2 will not become 2, rather it will remain 3 after this introduction as well. So in that fashion, what you are basically saying is how many maximum number of elements that I can need to create a particular value. So now if I ask you, okay, for creating 7 with first 5 elements with k equal to 2, is it feasible or not? So what you can do, you can simply look at the min array for the first 5 elements. The min array for 7 would be less than equals to 2, so it is within this range, and the max value should also be like around 3, so this is also within this range. So you will simply be able to create your create this particular value with the given set of k elements. But if the min value is itself greater than 2, let's say the min value was 3 here, or you are asking for this first 3 element instead of first 5 elements, then the min value is 3, but you want to select only 2 values, so it is not feasible. You return false here, right? So hope this entire thing is clear. If anything is unclear here, would encourage you to rewind and watch the dry run again, and I'm very sure you'll be able to get it. I'm not showing the dry run for the max value, just for you to try it out by yourself as an exercise. The final algorithm, if you combine everything, would look something like this. So remember how we started. We started with this particular algorithm wherein we are trying out every possible left and right OR and see if they are possible. I will take maximum with the current XOR value. Now for figuring out whether a left and the right OR is feasible or not with a particular k element, we first figured out the minimum number of elements required to make a particular OR value with a particular set of prefix elements. And in the same fashion, we will figure out maximum number of elements required to create a particular OR value with a sum prefix elements. So once you have both the prefix array built out, you can simply check the min steps of the prefix and the max steps of the prefix. The max steps should be greater than equals to k and the min steps should be less than equals to k. If both of them satisfied, you will simply return true for the left part. In the same fashion, you can create a suffix version of it for the right part and check the exact same inequalities to determine whether the right part is feasible or not. And once you have figured out this for a particular bisection or for a particular intersection, you can simply check whether both left and right are true or not for that particular separation. If it is true, you will simply return true. If it is false, you will try out the next possible separation and again exactly do the same thing. So what is the overall time complexity? You had two loops before that will take order 2 power 7 multiplied by 2 power 7 time for left or and right or. Now this is possible. This is possible will take will iterate over all the separations so that it can take order and time. And inside this you are doing some order 1 operations. So that will simply be order 1 operation. So overall complexity is 2 power n multiplied by 2 power n multiplied by 2 power 7 multiplied by 2 power 7 multiplied by n plus the complexity required to create this min steps, max steps, suffix min steps and suffix max steps. And for all of them you just need n multiplied by 2 power 7, right? So you will simply multiply this by 4 and this entire thing is like kind of negligible in front of this. So you can simply ignore this and this is your overall time complexity, which will easily fit within the given time constraint. So if you have watched to this point, I would strongly encourage you to code. The code should not be difficult. This is exactly what you need to do. Along with this, the only thing you need to figure out is how to do the same thing for the suffix part, which should be almost analogous. So I would encourage you to pause and try to get it accepted as well before moving forward. So let's look at the code. The code is exactly what we discussed. We start with all the possible left or and right or, and then we'll call IsPossible function whether we can select k elements such that the OR value is this, and then we can select k more elements such that the OR value is this. If it is feasible, else or R is feasible, and I will include that in the computation of my answer. Now what is IsPossible function? Again, exact same thing. We'll try out every possible separation. Basically we have to separate the left and the right part, so we'll try out every possible separation, and for each separation I will check whether it is feasible to make the left part to select k elements from the left part such that the OR value is this, and is it feasible to select k elements from the right part such that the OR value is this. So we'll simply look at the prefix and the suffix array, and this prefix array stores a pair. The first value denotes what is the minimum number of elements required to make this particular OR value, and what is the maximum number of elements required to make this particular OR value. And if k lies between them, it's all good. Similarly, if k lies between the right part as well, it is all good. If both of them satisfy, we'll simply return true. Otherwise, we try out next possible bisection of the two left and right part. Now, Before all of this, we had called compute function, which is simply computing this prefix and suffix array. What we are doing is exactly similar in the prefix and the suffix part. Only difference is in the prefix part we are moving forward, and in the suffix part we are moving backward. Now we know that the whatever existed for the previous one will exist for the current one as well. In other words, whatever subset that was there, you can simply take on that subset one step forward, or you can append AI to them, right? So if you don't do anything, exact same thing will move forward, and the values of this will exactly be the same as well. After that, we initialized prefix of j, the first value of it to 1, which is basically the minimum number of steps required to create array of j from the first j elements, which will always be 1 because we already have array of j with us, right? And what is the maximum number of elements required? Maximum number of elements would be whatever was required, comma 1, because this might just be the first instance of this itself. You might not be able to make array of j before, so it's important to get this initialized as well. After that, you will simply try out all possible values. If it is not feasible, you will simply continue, or rather if it was not feasible before, you will simply continue. If it was feasible, this is the new value that you can now make, right? And you can simply calculate the min and the max value accordingly for this new value as well. The same way you will do the suffix part as well, and once you have both the things, you can easily answer this in just order one time in IsPossible function. So hope the entire thing is clear. If you have any doubts in any of the pieces, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.